Good evening, everyone, and welcome to the fourth lecture hosted by NUS Cities. Just a housekeeping tip, please ensure your devices are on silent mode or on powered off, because there are microphones on the ceiling which actually pick up the slightest of the noises. For those who don't know about NUS Cities, we are a university-wide, multidisciplinary, open and inclusive collaborative platform hosted within the College of Design and Engineering. Through our collaborations with local and international institutions, we hope to create synergies that extend within as well as beyond NUS. The lecture series will investigate policies, ideas, and projects developed by urban experts which aspire to create sustainable, resilient, and livable cities. Through the lecture series, we hope to create a platform for discussion, retrospection, and conversation to give momentum to the ongoing research and exploration regarding issues concerning cities. I would now like to introduce our first lecturer for the evening. Professor Michael Batty is the Bartlett Professor of Planning at the University College London, where he is the chair of the Centre for Advanced Spatial Analysis, also known as CASA. Prior to his current position, he was the Professor of City Planning and Dean at the University of Wales at Cardiff, and then the Director of the National Center for Geographic Information and Analysis at the State University of New York at Buffalo. He is a Fellow of the British Academy, the Academy of Social Sciences, the Royal Society. He is known for his monograph, Cities and Complexity, The New Sciences of Cities, and Inventing Future Cities. He's an expert in the use of computer models to guide urban planning, analyze cities, and explore what they could be. He's concerned with the issues of the unpredictability of cities and how these can be met through modeling to tackle issues of urban resilience, such as the recent COVID pandemic. Please join me in welcoming him.
Thanks very much for inviting me. I'm going to talk about the complexity of cities in a different way, I think, from what Lewis is going to talk about, from the bottom up. To some extent, I'm using the idea of digital twins, which has become particularly popular in the last 5 years as a term. Of course, like all of these sort of terms, nobody can quite define what a digital twin is. I'll have a go at defining a digital twin. But one of the kind of key things in the talk is that the idea of digital twin is really, to some extent, more than one model of the same thing. And in a way, that really belies this whole fact about complexity in cities. If we can have more than one model of the same thing, and that an individual might be able to build more than one model, more than one perspective, basically, then that's the kind of lens on complexity that we've not really looked at very much in terms of the science of cities. Largely, I think, because computers and data have not got to the point until very recently where we can actually build more than one model in this context. If you look around Singapore, I think that you have had more than one model built of transport, but I don't know at any particular point in time that you have two models running, as it were, side by side, and to some extent competing with each other in that sense. So this is really what the talk is all about. If you want to actually look at the slides, then that tiny URL should take you to the slides themselves. So if you don't want to hear me, you can sort of just put it on your phone or something like that. So those two things will do that. I'll give you that at the end, basically. But if you want to take a photo, then please do. Or if you miss it, then I can explain it at the end. Okay, so what am I going to talk about in this talk about digital twins? I'm really going to talk about models. To some extent, to me, a digital twin is a model of some sort. And models, of course, are abstractions, they're simplifications. And the idea of the digital twin being as close as possible to the real system, is to some extent a contradiction in terms when it comes to thinking about theories and models in this particular context. So I'll talk about that, a few words on that as preamble, and then the idea of twins as models, the idea of twins as controllers of a system, etc. And then quite an important concept that although we may have a model and we may have a real system, we always have ourselves as model builders or stakeholders, as model builders or model users, basically, in the loop, basically. So humans in the loop is really all important. We can't really talk about models and real systems and twins and so on without actually considering the way we interact with them and them in that sense. So where do digital twins come from? I'll say a few words about that. I'll then digress and talk a little bit about some excellent examples of twins. The idea of a map as an analogy, a map getting closer to the real thing, basically, is again an excellent example of some of the conundrums, some of the paradoxes, if you like, of what the digital twin idea is all about. And then what I'll do in about 15 minutes' time, because I'm conscious that we should try and keep the thing to about half an hour. I'm going to look at some examples beginning with non-digital twins, because although we might talk about digital twins, when we begin to unpack it, we find there are many non-digital aspects of using them in that sense. Then I'm going to talk about 4 very different examples and types of twin in the same location. It so happened that in our group, a number of us are building models of different things, basically, and when we took a look at some of our models, we realized that we were modeling the same place, and that place in London is the Olympics 2012 site, which is in Stratford, basically. So we have 4 different models of what goes on at one particular point in that site. Our models, in fact, deal with a much larger context. So we have a national model, basically, a national land use transportation model, but it covers the Olympic Park. That's one zone in it. And we also have a BIM, basically, which is one of the buildings at the center of the Olympic Park called Heres. So I'll tell you about 4 different types of model of the same location, with a view to the fact that if you're developing a local plan or a development plan for that part of the world, then probably you would have recourse to use any one of these 4 models or all 4 models in a sense together. And that raises this question of how do we reconcile different models which might be telling us different things about the same thing. So we'll look at a 3D city model that relates to our long-term model in CASA, which we started building about 20 years ago, which is a kind of classic 3D model. There were perhaps about 20 of them. Well, maybe I think there were 60 of them in existence in about the year 2000, and now there's 6,000 or 60,000 or 600,000, basically. It's very, very easy to build. So I'll talk about our 3D model. I'll talk about smart buildings and BIMs. I'll talk about our ABM transport model, because the transport system cuts through this area. And then I'll spend a bit more time talking about long-term urban change. We have a model that is scaled to the UK in some sense, and again, that's another example of how computers and data have got to the point where we can scale these things, and I'll talk about that. And I'll say a little bit about our quant model, which this national land use transport model, in terms of scale changes and network changes. Now we have this model, we're beginning to actually tweak it and build different variants of the same things, different twins, if you like, of the same thing. And that raises a whole issue. And then a couple of concluding remarks about what next. Okay, so we all know that computers have changed the nature of how we theorize about the physical and social world. We've got this opportunity now of building many different models of the same phenomenon due to increasing computer power as well as new data sources. And into this melee has come the idea of the digital twin. It dates back a long time, probably about 20 years, but computing and data have driven it very fast in the last 5 years. And of course, the term is riddled with ambiguity. It's highly evocative of our wishing to get as close as possible to the real thing, but of course, in some senses, we can never actually reach the real thing, etc. If the model gets as close as possible, it ultimately becomes the real thing in that sense, and therefore that really relates all of these issues about the semantics that we're using in this sense. There's various definitions of digital twin. This is taken from something that was produced by the Center for Digital Britain in the University of Cambridge, the Building Smart report, and I'll leave you to read that. But essentially, this is a definition that really relates to the fact that it's making the point that the digital twin, the digital model running alongside the real system, one of the kind of key features is that it swaps information with the real system. There's two-way traffic. And of course, in some senses, if you're building a digital model, for example, of a production process, in a sense, which may in fact be also digital in some sense, then the two interact in a sense in terms of control, in terms of feedbacks between the model basically and the real system, and vice versa in this particular context. So that definition is of this. But we'll see that when we move away from the idea of really a very tangible and well-defined process towards the kind of thing that we think about in cities, then this notion of the twin being close as possible really is something that is quite problematic, basically. So many people would say, having heard me so far, that a twin is no more than a model, basically. And it also implies that in the future, multiple models of the same thing will become the norm. That's another theme in this particular lecture, the idea of multiple twins, thereby invoking this ambiguity. Now, the many models of the same system school has been anticipated for many years. There's a great book by the Russell Sage Foundation by Greenberger, Cranston, and Chrissy in 1976 called Models in the Policy Process, where in that particular book they talk about what the Federal Reserve are doing in terms of building a whole series of models to look at the economy, counter-modeling in this particular context, different econometric models. The same is true in terms of weather forecasting, ensembles, if you like, of models in this sense. There are lots of people who have talked about this. George Box talked about it. Scott Page has a book called The Model Thinker. Dirk Helbing, who you know from Future Resilient Cities and the CREATE program here, has written about it. And George Box, who was an English statistician, he articulated it rather well when he said in the 1970s that all models are wrong, but some are useful. And really, we should have that engraved on our arm, basically, or tattooed on our arm, I should say, at this particular point. All models are wrong, but some are useful. It's a big question, basically. And if we have more than one model and all are plausible in some sense, different degrees, but how do we use them? How do we integrate them? And how close are they to the real thing? So this is really one conclusion. It's not very profound in a world where we clearly can have more than one model of the same thing, but nevertheless it's becoming the norm in some senses. Okay, so quickly then, twins linking models, twins as controllers, the human in the loop, basically. Of course, in a model, we throw away a lot more than we keep. In fact, arguably, the best models are the simplest. It was Einstein who said something like, everything should be as simple as possible, but not too simple, something like that, he said. Various people have talked about simplicity. And therefore, we might be able to have one models, many twins in this sense, but it's slightly weird in the sense that we really need to begin to reconcile them in some sense. And how can a model be produced as a literal twin? This is to some extent far too close for comfort. Now, a basic definition of the digital twin, as we've seen, is the idea that the twin actually swaps information to some extent. And of course, the ultimate example probably of the digital twin is indeed a computer. I mean, Turing and von Neumann both said in the late 40s that computers were universal machines. They could simulate themselves. So probably the best example of a true digital twin is indeed a computer in that sense. Okay, so there's a very good example, I think, in a book by Gordon Pass called Approaches to Cybernetics from the late 1950s. A very nice cartoon which pictures this idea of the digital twin. This is from his book. Pass was an English cybernetician, along with people like Ross Ashby and so on, Stafford Beer. He wrote a book in cybernetics. He did a lot of work, actually, within architecture as well as in cybernetics. And this is a cartoon from the book. And this contains everything that really is in the modeling environment. We've clearly got the humans in the loop, the model builders or the stakeholders watching the model. We have the model itself in a black box, basically. Inside of that is a traffic system, of sorts, basically. We're sensing the traffic system using a variety of wires, basically, sensing that. And if we really want to pertain to the old world, we actually look through the window and we can actually see the traffic moving, basically, in that sense. So all of the elements, if you like, of the digital twin are contained within this. So how close is this to the real thing? Well, to some extent, in this context, we have the real system and we have the digital twin. And in terms of the definition, we have interaction between the two. So we have the real system influencing the digital twin, providing data for it, and then a feedback loop, which may be positive or negative in that sense, either in a particular context or both in that sense. So the system is joined in some sense, and we can apply that idea to all sorts of things. You see, we apply that idea certainly to digital twins of aerodynamic systems and so on, all the way through to digital twins of cities. There is something out there, several elements out there relating to digital Earth, for example, which is a long way away from the idea of a physical artifact such as an aero engine in that sense. And human in the loop, adding that into the particular context, and then we can have a whole variety of digital twins. These are our different models, basically, and of course the big question is, how do we integrate them? There are indeed multiple ways of doing this. Okay, if you used to be able to, right at the beginning of computing, actually get inside the loop. This is a picture taken from a book by Bhattacharya called The Man from the Future. Now, The Man from the Future was John von Neumann. It's a very good book, actually, very readable. And in that, there's a quote by a mathematician, Harry Reid, who joined the von Neumann project in Princeton at the end of the war in about 1950. And he basically talked about the ENIAC, which was one of the first digital computers at the Moore School in the University of Pennsylvania. And you can see that the operator inside there is not only fixing and building the machine, the operator is probably also actually running a program at the same time. So this idea of being inside the thing, and of course the evocation here is the idea that the machine is now the city, and we're all inside some kind of computational context in that. I'm not going to push that too far. I can't elaborate it in any particular way, but you can think about it. It's really quite important. Are we moving back full circle? Okay, now very quickly, a couple of properties. Michael Greaves, who is accredited with the idea of the digital twin. The digital twin is like the smart city. Who first coined it? Well, you can go back indefinitely, probably Plato or Aristotle or something like that. But the digital twin basically is associated with a production engineer, Michael Greaves, who wrote a paper in 2003, but really didn't put it into the public domain properly until 2014 in that sense. And the best example in our world of the kind of Michael Greaves digital twin is an actual building information model system or management system, in that sense, a BIM, basically, a model of a building that is not only relates to the construction of the building and its parts, basically, but once the building is complete, then the software that is used to build it really becomes part of the building in terms of its maintenance and control in that sense. And that's one of the examples we have at the Olympic Park in West London. So a list of properties. Digital twin can't be a mirror image. It may be a replica. It cannot be the same as the original, or can it? So these are all question marks. They depend on their media, and if the media is close to the media of the original model, it might be a digital twin. So if the real system is digital and you have another digital model alongside, then how close is that? Can a digital twin predict a future that does not exist yet? A digital twin is always a coupling, as we've seen, a transfer of information, and it might be a controller or a mechanism to be embedded in the system. In the 1960s, there was a very strong development of ideas in urban planning called the systems approach, basically, and a couple of books were written at the end of the 60s called A Systems Approach to Planning or something like that. And in one of them, the book by Brian McLaughlin, he suggested the cybernetic structure, the idea of cybernetics as a controller, could be used as a model of the planning system. So to some extent, these ideas are not new. They go back a long way, but with a different kind of terminology. How can digital twins be compared or validated? We sort of need a Turing test for digital twins in this particular context. And I'll go over this rather quickly, but basically a Turing test a Turing test of anything, probably, even the kind of thing that Turing, in fact, suggested it should be used, is probably not passable by anything in a sense. But basically, if two models are the same, and all you have is the output, basically, are they the same? And we know almost without thinking that two models will never quite be the same, basically, in that sense. There will be differences of a sort in this particular way. Okay, how am I doing for time? Where's our host? How are we doing for time? We're okay, are we? Okay, you're probably going to tell me when we're 30 seconds to the end, but okay, let's quickly look at a digression. There's some great examples of digital twins as maps as analogies. Now, the one I like the best is by Lewis Carroll, who is the author of Alice in Wonderland and so on. In his last work, Sylvie and Broody Concluded, he tells the conversation between himself and a German gentleman about making a map close to the real thing. Now, in my youth, I could actually perfect a very good German accent, right? But I'm not going to try it here, basically. So let me just read it out. This is a conversation between myself and Mein Herr, basically, the German gentleman. What a useful thing a pocket map is, I remarked. That's another thing we've learned from your nation, said Mein Herr. Map making, but we've carried it much further than you. What do you consider the largest map that would be really useful? Me. About 6 inches to the mile. Mein Herr. Only 6 inches, exclaimed Mein Herr. We very soon got to 6 yards to the mile. Then we tried 100 yards to the mile. And then came the grandest idea of all. We actually made a map of the country on the scale of a mile to a mile. Me. Have you used it much, I inquired. It has never been spread out yet, said Mein Herr. The farmers' objective, they said that it would cover the whole country and shut out the sunlight. So now we use the country itself as its own map. And I assure you it does nearly as well. That's not a good advert for abstraction, basically, in that sense. But nevertheless, it's quite interesting. Now, lots of people have talked about this. There's a Polish scholar, basically in 1931, I'll tell you, Borges, Bateson, Joan Robinson, the economist, even D.H. Lawrence have actually talked about the idea of the map being more real than the actual land itself. If you look at the English patient, then Ralph Fiennes, basically, in the movie, has Herodotus, the histories, basically, which is almost his kind of, digital twin, basically, in a sense. So, of course, Louis Borges, in his essays on exactitude in science, he tells the same story of cartographers so obsessed with their art they decided to produce the most detailed map of their empire that they could make at a scale of 1 to 1, basically, in that sense. My colleague, late departed colleague Lionel March from the University of Cambridge in 1974 talked about all of this, basically, in a sense, and I'll just give you one quote before we move on. He basically said, in the yellow there, all models to be useful must be selective, and if you like, false to the reality in some respect or other. Pocket models may be the most useful in the end. Okay. Right, now let's move on to our 4 very different types of twin to give you an idea. So I'll quickly go through these. They're fairly impressionistic, etc. So I'm going to talk a little bit about 3D cities. We've had a model running for about 20 years which has been improved and changed in lots of different ways so that they are twins of each other in a sense. I'll talk a little bit about our smart building example. Then I'll talk about our agent-based model of traffic in London on the subway system, on the tube, basically, and then our LUTI model, our quant model, which is low-frequency thinking in terms of cities, simulating relatively long-term growth and change. We're talking about growth and change over a period of about 10, 20, 30 years. But it's not like the flows of traffic, agent-based modeling, which is what's happening in the next, 10 seconds, 20 seconds, the next hour, and so on the subway. Okay, now there's lots of things we've written on models, basically. We're very proud of this paper, The Role of Complexity for Digital Twins, which has got all the bits that you're supposed to be learning about in terms of complexity here, etc. And you can see that our friend Dirk Helbing is a co-author. Don't look too closely at that paper because it was written by a committee, basically, by people emailing each other and adding bits to it. So in some senses, it's an advertisement for the fact that we need to think about complexity and digital twins together, basically, in that sense. So again, that's got some food for thought. Now, my own non-digital twin, just to show you my credentials, a number of people that, when I came to NUS Cities the other day, introduced me as a geographer. Lewis introduced me as a geographer. I'm not a geographer, I'm an architect planner, basically. And to show you my credentials, this is my non-digital twin in my second year in the architecture program, and God forbid anybody would build this stuff. Of course, it did get built. This was in the early 60s. It did get built as part of the public housing program, but fortunately, a lot of it has been torn down since then, basically. So there's a moral there. So non-digital twins are important in that sense. They're still important to thinking about how we use these models, basically. Now, this was a picture I took the other day in the Bartlett. They have the summer exhibition at the moment in UCL, and these were the models that I don't know which year was building, but there's some really very elaborate-looking physical models, basically. Here is a model which is a mixture. This is the London model in the Corporation of London, and you can see there's bits of information technology within the non-digital model, basically. You can do simple things like press buttons and buildings light up, and you can see the gherkin and the shard and all this sort of thing in that particular context. But it's a useful digital and non-digital engagement in this particular context. And last but not least, this was a project we had in CASA, and you can see this is our London data table with the street network and on this. And this was actually designed to simulate the London riots, basically, the Tottenham riots at about 12 years ago. And in the corner there, nobody will recognize this, but the most famous person in CASA is that lady there. She's a BBC TV star, Hannah Fry, who runs the Mathematics of Cities course in our centre. Okay, so let me move on. These are non-digital, but merging towards, part digital in this sense. Now, the four models in question, I'll go through them very quickly. You can see that the building at the top right there, basically, where it says here East, that's the building that used to be the media centre. It was then taken over by, it's taken over by the Olympic Legacy Corporation, basically, which covers the whole site of the Olympics. But it's one that people in UCL are wiring. A BIM was not built when that building went up in 2012. It's been added afterwards, basically. So, and you can see, you can't see, I don't think I have any slides, but in the building, you can actually. If you go down one, you can see a little sensor. This is the sort of stuff that's been placed in the building. So there is now a building information system that's both monitoring it and controlling it in some sense, and some of the construction is related to that, which is to make the building a little bit more intelligent. You can see the example of our 3D model, very different from the original 3D model. There's a mixture. Vilo means virtual London, and this is the Olympic site, which is taken out. It looks like as though it's on a table out here, for example. In fact, it's not it's a digital model entirely, and it's been placed actually within a particular digital screen of some sort in a way. You can fly around it, and also there's real-time data working on a different time scale from this running through. You can see tube lines and so on. So that's Andy Hudson-Smith's work. This is John Reeds, who did work, and he's now our new head of department, so he's got no longer any time to work on this sort of stuff. But John did do some work when he was a postdoc in CASA about 10 years ago on the London tube system, and we have very good data from the Oyster card system, the smart card. We have about 20 years worth of data. London Transport won't give us 20 years of the data, because if we had 20 years of the data, we'd be able to say all sorts of nasty things about patronage in subway stations. They don't want us to work out what subway stations are losing patronage or gaining patronage. It's a very big political issue in that context. But nevertheless, they're very good at giving us tranches of this data so we can actually build agent-based models. And last but not least, the pictures on the right show you different models. The little white dot really represents the location of Here East. And so all of these models are potentially useful to thinking about a plan for the Olympic Park area. That's really the message in that sense. And how do we reconcile them? Now I'm going to tell you how we reconcile them. In some sense, we're still learning about dealing with them, because different groups of people in the centre with different skills have actually been responsible for building these. Okay, now let me talk about our long-term urban change model, because this is where we can begin to tweak it. Now, I'm not going to give you a tutorial on how these models work. To cut a long story short, we feed them with employment in different locations. These are locations based on one of our census geographies. There's about 1,000 of those sort of zones of that size in the Greater London area. And the model basically moves employment and population. If you'd like to think of this as the journey to work, and I like to this as these are the flows, and we build various sorts of models that control the flows. Gravity models have been very well known for many years, basically, but we can build discrete choice models like the ones built in the Sim Mobility project. We can build a variety of different models of this, and we can sort of have an economic component, basically. So this is the model we've got, and we scaled this model to the UK. We've scaled it to the UK for the simple reason, we've scaled it to the UK for the simple reason that many of the problems in British cities can't really be handled by the cities itself. A good example is the high-speed Elizabeth line, which runs from East London to West London. The digital footprint, the footprint of that particular line is right throughout the rail system, the savings in time in that sense. So in a way, to look at these big infrastructure projects, or even to look at quite small ones, they have repercussions outside of the system, outside of London, outside of Birmingham, and so on. So we've built basically a model of England, Scotland and Wales. Northern Ireland is not there because we're anti-Irish or anything like that, for God's sake. Northern Ireland is not there because, by and large, this is a physical model that moves people around, and it's very difficult to actually move people on a very different mode of transport, as we'll see in a moment, from, northwest, from Liverpool, basically, across to Belfast or Dublin, basically. So Northern Ireland is excluded from this. But we scaled it up, and you can see that in that context, we've also put the model into a web-based version. So if you click on the link, basically, then you'll see that we've actually got, you can run this model on the web. And in some senses, the server side is all of these web services that are now important. The model itself is quite a tiny bit of the whole lot. And then on this side, we have the visualization using some standard products such as Mapbox and so on. And then for digital engagement and so on, we've got various sorts of media of that sort. Okay, let me quickly go through. This is what you see if you actually log on. In fact, this is just the England and Wales version that I'm showing here on these slides, basically. If you keep zooming in on that, it'll refresh and give you the boundaries. That's the link, basically. So if you type that into your phone, don't do it now, please, because it's not, it's not designed really for a phone. You can run it on the phone, but it's much better to run it on the desktop, basically. It'll really screw up the graphics on the phone, sort of, one part of the country will appear on the other side and so on, in that sense. Okay, and this is typically what we do. This is Merseyside, and we can inject jobs. What I've done is to inject 40,000 jobs into one of these areas here, basically Knowsley, which is a very poor part of Liverpool, and they've never seen 40,000 jobs in Liverpool. I mean, it's just amazing. But anyway, all of this does is work out where the population goes. That's a very simple scenario. You can almost guess it, really. These things come into their own when we're talking about 10 different locations of population, how the networks change and so on. Let me move on. This is an example of how we use the model. This is the Elizabeth line, runs all the way from Shenfield in the east, basically in Essex, on the Essex border there, all the way through to Reading, basically, which is a very fast line. I mean, many trains, it's a very popular line, basically, in that sense. And the footprint, in terms of the influence, you can see. Of course, it's connected to the national rail system and so on. You can move around. So if you're in Newcastle and you're travelling towards Brighton, say, at the top to the bottom, you pass through, you might use a little bit of crossrail, so that will change your travel time, basically. And these are pictures of the displacement of population, the internal migration of population from the line. Okay, conscious of time, what we've done in this is to suggest that when we've got the model, basically, we can then begin to tweak it. And we've actually built the model for basically what this census geography here. The square in the middle is the City of London, and the other square, the rectangle, is the Olympic Park. But we built the model for this level, which is called MSOA, middle level super output areas. We can move to lower super output areas, which is at this level here. So we're moving the model from something like 8,000 zones in Britain through to something like 41,000 zones at that level. You can see here so exactly the same model, but with a completely different level of resolution. It brings all sorts of problems with it, basically. So in other words, 4,835 LSOAs in Greater London and 983 MSOAs. So the model is working at MSOAs for the nation, and we do it in this way. Of course, one of the kind of key things is that when we're talking about 4,800 LSOAs, and we're talking for the whole of Great Britain, 41,789, we need to square that number to find the potential flows, which is something like 1.74 billion. Now, that's a really big problem. It takes 30 seconds to run the simple model, and it takes something like 8 minutes to run the big model, basically. This is for the UK. Okay, and this is what we can do. We can simply just replace that and look at the difference. And, in fact, the differences are very profound. The one statistic I'll just pick out is that the bus system, the average travel time for the simple model with the 4,800, the 8,500 zones is 21 minutes. When we move to the level with 41,000 zones, it drops to 15 minutes. Now, why does it drop? These were sort of unanticipated. If we'd have guessed it, we could have guessed it beforehand. But the fact that it's dropped is due to the geometry of everything. The geometry makes an enormous importance. We didn't think the geometry would make so much importance. Now, we've lots of geometry in this sense. You can see that the comparisons are quite good. There's about a 96% correlation between these two maps, one at the MSOA level, the other the LSOA aggregated to MSOA. So you can see there's a fair bit of correlation, basically, in a sense. But nevertheless, it's really in no sense giving us the same model, basically, or the same results. Now, the other digital twin that we've built is we've added, and we've only just done this a couple of weeks ago, we've added in a walking layer. Our model is multimodal. It's got roads, it's got buses, and we've got rail, basically, and you can see that the little V here is the number of nodes, so 3.5 million nodes and 8 million links, basically, in the Ordnance Survey road network. Over here, for rail, basically, 3,000 stations, basically, and 10,000 edges, links, so massively different. This one, which is the walking network, that was put together by a couple of our RAs who used OpenStreetMap and the Ordnance Survey data and some other bits, and that's about 20 times as, maybe 10 times as dense as the actual road network, basically, and that is leading to all sorts of problems. What happens if you're out here in an MSOA, somewhere like that, in West Wales, basically? How do you actually calculate? There might be 2 or 3 people in the census who are walking. How do you calculate what the distance is? So some of our rules are being changed in that sense. So these are the problems of tweaking our digital twins. Now, I'm going to go over that very quickly, just showing the results. Okay, let me just finish it off. Is the concept of the digital twin useful? Well, I'll leave you to judge that like many things, the answers are yes and no. It forces us to think about how cities are changing and how models are proliferating. How do we deal with many models of the same problem? The idea of federated digital twins, many twins, in the papers that have been written in lots of different areas about this idea of more than one digital twin is really gaining ground in many senses. It forces us to think about what smart cities really are, which is, of course, part of the wider debate about what cities are in this context, and how they're being transformed by new technologies in that sense. You know, what happens when we've got large numbers of digital twins that are genuinely different from each other and lead to enormous conflicts. Some of these things are important. And it forces us to think about what a model really is, basically, and how we can link many models together, and how we can think of many models and different conceptions of the system at the same time in our heads without actually going mad in that sense. Okay, thanks for listening. I've written 3 editorials in Environment Planning B, and these are the titles of them. And we wrote a paper in the book Digital Twins for Smart Cities, edited by Jennifer Schooling and Lee Wan and so on, over at Cambridge, basically. We'll have a lot of work on this. That's it. Thank you very much.
Thank you, Prof, for that very interesting lecture. We'll now be taking a 15-minute break, so please be here by 6:55. Yeah. Welcome back, everyone. Since we are running late, we're just going to start now. I would now like to introduce the second speaker of the evening. Prof. Louis Bettencourt is the Professor of Ecology and Evolution at the and Associate Faculty in Sociology at the University of Chicago. He was also the inaugural director of the Matsumoto Institute for Urban Innovation and external professor of complex systems at the Santa Fe Institute. He's the author of over 100 scientific papers and several edited books, and has been featured in leading media venues. Prof. Bettencourt has worked with the UN and NGOs such as Slum Dwellers International, SDI, to pioneer ways in which mathematical analysis of slums can empower communities to create better networks in their urban environment, making services accessible and socio-economic connections possible. He is an expert in the use of mathematical models and complexity science to analyze the structure of cities and how they create and can be made to facilitate the potential for socio-economic interactions that produce knowledge, innovation, and creativity. Please join me in welcoming him.
Okay. Thank you for being here, everybody, and staying and so on. So as you heard, I'm not an urban planner. I come at this from a quite different point of view. I love cities. I grew up in a city in transformation. I was always very interested in the problem of human development. How is it that cities actually channel transformations in human societies? I'll make the case that we don't know how to do it in any other way. And so from that perspective, how cities work and how they manifest who we are collectively. So that's what I want to talk about. But you may know that Mike and I, we do this fairly frequently, back to back. And so, but it varies every time. So it's amusing, I think, for both of us. But my talk will in some sense, show that we have different pedigrees. I come more from the natural sciences, but I've been very interested in cities and human social dynamics for about 20 years. So you'll see that. So these are my coordinates and so on. I'll get back to these towards the end. But I just want to say this is the work of many people. Many of them were here in Singapore for a little while. But mostly this team also includes more people that I cannot show a photo. But a lot of them assembled at the Santa Fe Institute and then at the University of Chicago. So what I was starting to say is that we're here actually this time around because we were here as sort of advisors to your new programs at NUS on cities, NUS cities. And so the question really was, and we spend a couple of days talking about urban science and what it is and what it isn't. So I thought I'd bring that theme sort of a running theme for the conversation today for my talk. And I want to show you a perspective that maybe is a little different from at least what Mike showed today. That's not so much about models per se and a tradition of simulation and so on, but it's more about really something that I think in my mind, in my life, very special happened in the last 20 years, which is that we have gained access to evidence and data. You can visit, you can talk to people all over the world, and we see all kinds of different urbanization. And that has led to a revolution in understanding what cities are, what they do, what's common to all these cities. That has enormous scope, and it will allow us to see all kinds of things all the way from the first cities into the future, but also across many different scales, all the way down to fundamental aspects of human behavior. And it's the ability to predict these things that really constitutes a science. So I want to tell you a little bit about that. But it's also a different attitude, an attitude of paying attention to the phenomena of cities and try to understand how they work, which flips around some of the issues about urban planning and the use of technologies. So I want to start, therefore, to tell you something about what is not urban science. Okay? So here's one thing that's not urban science. I apologize if you're Swiss. So, so this is one of the most famous. You've seen this. I apologize. It's a little grainy. The slides went through the different machines. But this is a very, very famous scheme. It's kind of the poster child for the modernist city, right? It's Le Corbusier. And there's this idea of building cities that are very efficient. They're very efficient because they move a lot of people around, in this case in cars and highways. And they pack a lot of people in towers on the green, as they were called at some point. So this is not a city, because even though it's spatial, and you've seen cities a bit like this, it really doesn't pay much attention to people. I mean, they're like little ants there, or their interactions, or what they're doing. This is so the consequence of that is that this is a terrible idea, right? This is not even science, junk science, right? Forgive me, but that's what it is. It created terrible cities where it was done sort of literally, created places that really hurt people and held them back, and that in many ways doesn't endure as an urban environment, as a built environment. Eventually gets demolished or modified. So this is not a city. This is also not a city. This is one of the prototypes, there are many, for a smart city. This is more or less today. This was a case for Alphabet or Google in Toronto. There's a very famous recent story, almost a soap opera about technology in cities that played out in the last few years. And this story in particular tells you about when they decided to finish. But the idea is that if you know Toronto, right? Toronto is an amazing city. You can do no wrong in Toronto, right? It's just thriving. But they did. I mean, they had basically a district that was supposed to be fully optimized using technology and so on. And Toronto hated it eventually when they realized what Google was trying to do. And here's sort of a second piece on that. So Toronto decided, I like this title because it's provocative, but it decided to say it wants to kill the smart city forever, okay? Forever. So why was that? Why was that not a city? Why was that so bad that they want to kill it forever? It was so antithetical to what a city is. And the reason was that it was all technology and built environment. It was sensing everything, it was optimizing everything. How is that a city? How is that to do with people and the things we do and the interactions we have? It doesn't mean that these models of cities cannot house them. People are very resilient, right? They can live through all kinds of things. But it was not the right thing to do. And it was against the civic spirit. Civic means of the city, as you know, in the original meaning, of a great city like Toronto. Okay? So these are very important models. Urban planners are playing with these ideas, technology companies, big builders and designers. They use these ideas. But how is this possible? That we'd spend so much money, that the biggest companies in the world, the most famous architects would come up with ideas that are so wrong about cities, that would hurt so many people, set back so many lives. Isn't that crazy? This should not happen, right? And why did it happen? It happened, I would say, so this is where the science comes in, right? A lot of people have a conception of science as something that's lots of maths and models. It's a book and tells you what to do. That's not what science is. This is what I want to say now. So this is a quote from Carl Sagan. I should say he's an alum at the University of Chicago, a very famous one. You may know him from Cosmos and so on. But the idea of this quote is the first idea that I want to introduce about science, an urban science, if you will, which is that science is more than a body of knowledge. I'll tell you about a body of knowledge and what we've learned about cities in a little while. But it's a way of thinking. And the subtitle says it's a way of skeptically very important, interrogating the universe, or the city, with a fine understanding of human fallibility. If your planner doesn't have a fine understanding of human fallibility, particularly their own, you may want to move. Think about that, right? So if you want to design and influence the lives of so many millions of people, you have a special responsibility. You have to think about what you're doing and whether they're facilitating their lives or making them harder. So science is really a critical endeavor to try to understand how the city works. And what's happening here, what I'm invoking, what I'm proposing, is that you take the city, many people have said this, but you take the city as a phenomenon. We've had cities for the better part of maybe 6,000 years or more. They have happened essentially in every human society in different forms. They just exist. They are created, they go through cycles and so on, they change, they exist in many different forms. So the idea is that we should pay attention to what that is and what makes a great city and try to work with those processes, as Jane Jacobs once said. So in some sense, what I'm advocating is that this spirit of critical interrogation, asking questions, making guesses, seeing when they work and when they don't work against the phenomenon is essential if we are to create great cities in the 21st century under very dire circumstances of climate change, of population growth in some parts of the world, aging in others, and so on. So I want to go back to this theme and tell you about how we can get to start to understand what urban science is. What is this kind of knowledge that we may have of a city, or at least what are starting points and some principles. So the magic of it, I mean, this is not rocket science, right? But one of the ways to start doing this, Daniel Dennett, a very interesting philosopher, tells about key inversions of ideas in terms of how a science sometimes gets a paradigm. But this is not difficult. Instead of focusing on the built environment or the technology, let's focus on people first, right? And the reason to do this, as obvious as it is, sounds nice to say, but just is a thought experiment. Think the simplest city that you can imagine, an early city or maybe a very poor city. The city is not going to have the towers and highways that he was talking about, or the technology that Google's talking about, but it will have people, and they'll be interacting with each other, and they'll have some shelter and so on. So that already is a city, right? It just doesn't have all the other things that make life easier, but that is a city. It's that relational quality between people. So, so cities basically are not just people. They're really about people interacting with each other, right? So I'll come back to this theme, but cities are miraculous, like we're used to them because we live in them. But if you extract yourself from a little bit from it, any great city has things that no one really could explain to you. They were produced collectively by people working together in firms, in civic organizations, in governments, in all kinds of ways. And humans are able of that, of collaborating when they're put together in the same space to create things that are exceptionally interesting and new and valuable. And that's in some sense what cities are for. It's about the networks of people that enable those things to exist and be created in the first place. But the other thing that they also do, right, as we coming back to space, is that, so cities are places where people can be connected, see each other more or less every day. That's the scale at which a city works. But they also start building built environments that facilitate that, right? And these built environments, you know this, but just to say it, and I'll give you the essence of it, these built environments have certain specific properties. These specific properties are properties that allow those interactions to exist in the first place, you know, at minimal cost. So there are streets that allow you to move around in public spaces and so on. This is a very famous map for the architects and geographers, the Noli map of Rome. But they also start creating structures that have bigger roads and smaller roads and so on. And it turns out that there's a logic to that. It takes a little bit of math to see it, but I'll just take you through the argument in a moment. Now, we both love complexity, and we talk about complexity, but complexity in some sense from a human perspective is the simplest thing to understand what it is. It's not just complicated, right? It's that a human in an environment like a city needs a bunch of things. You can add your own or subtract if you don't like these. Here's a human, it could be you, it could be somebody you know, and you need a source of income, you need people to help with your kids, you know, you need a good environment, and so on. And all of these things are basically gotten from other people doing what they do and their organizations and so on. So this is kind of complicated. It puts you in a network of all kinds of people, all kinds of knowledge and function, right? You know this, that's the way you live, but I'm just saying it so that it becomes an analytical thing that you have in mind. And the way you get all these things is by going around the city, right? So this is my very poor scheme. See, if I was an architect, if I was a good draftsman, I wouldn't do what I do, but I can just about give you an idea. So you go around and you do a bunch of things and you accumulate a bunch of things as you go. This is a very beautiful idea. It's called the life path in time geography. But you basically accumulate a bunch of things that you have to do every day to maintain yourself, and then this varies a little bit from day to day. And over a lifetime, this changes so that you need different things that can accumulate knowledge, for example, and other things. So there's a picture of development, there's a picture of how the city works every day. But the point is that this thing is the essence of a city for all the people involved in interaction. And it exists. It's very important when you think about a network. We often don't think what it is, right? And I like to always tell my students, a social network doesn't really exist. It has to be put into space and time and has economic budgets and costs in terms of energy. It's a physical thing. And that physical thing is, in some sense, the scaffolding of the city. If you can describe it, if you see how it changes as you build or unbuild things and so on, you have a theory of how a city works structurally. I'll get to what happens dynamically in a moment. So I'm just going to show you a bit of, I know some of you are engineers, and I kind of have a background in physics, so if I have no math, I get nervous, so I'm going to show you a little bit of math anyway. But if you have a very simple settlement, this is just the simplest argument I can give you to show you some of the things I'm going to show you. These golden things are supposed to be houses. There's a certain characteristic scale, like a radius. This is an actual little town that was Aztec. And why is it not big? It's smaller. Why is it not bigger? And basically, people are interacting with each other, and there are people in each house. You can see that the number of interactions that they can have has to do with the number of people there, divided essentially by the area. That has to do with your likelihood of meeting people. And there's a cost that has to do with the length you need to cross. So when you put these two things together and do a little bit of math and so on, what you get is essentially something that has this nice property, that the city essentially has an area. The area of the city is related to its size, population size, but the area increases less quickly with an exponent of 2/3 relative to its population. And the number of interactions and all the things that result from interactions, all the economic transactions, all the diseases spread and so on, they go actually like this with 4/3. So this is what we call superlinear and sublinear. What's happening here is that as you put people together, this is a very unstructured behavior. I'll show you a little bit how to get the other behavior in a moment. But what's happening is that the city is compressing people a little bit. It's getting a little denser as it gets bigger. And this is allowing each person to have more and more interactions. And so, there's less space per capita, and there's more social products per capita as the city goes. And it turns out that this is characteristic of all cities. It's an interesting thing that happens that we call scaling, and that was one of the ways in which we understood many properties of cities. So I want to go a little faster, but basically, once you go to a real city, this is Mumbai, you need to consider how we actually built environments. There are sort of roads and transit systems and so on. And these are more structured. Those didn't exist in that scheme. This scheme actually doesn't predict the things that you observe. It's too big, that number. But what you can see is that these systems of mobility of cities actually have hierarchies. Like highways where you could go fast, or subway lines, so you go fast and it has a bigger flow. This is well known to transportation engineers, but this actually has a certain structure that's predictable in terms of what needs to happen, intermediate ones and local ones. And the flows tend to be larger at larger scales, but also they tend to jam on larger scales first, so you get traffic jams on top and so on. This is very schematic, but when you put this together, going through the math quickly, you have to go and read the book if you're interested. You basically get something that predicts an exponent which is close to what you see, this delta about 1/6, and that says that the cost of moving things around is superlinear, so it increases with population by 1 plus a number, and that the benefits will have that property as well. So the costs and benefits, as the city grows, they both increase, but they don't increase relative to each other. They maintain themselves the same. So you get more interactions, more money, you spend more money, you get more ideas and so on. You pay a bigger cost, but the whole thing can keep going because the fraction of the cost you pay is just a fraction of what you get. Okay, so this means that cities can exist in these interactive spaces between essentially certain states that don't make it too costly to move around, but that make the positive products of these interactions work well. But there are also exceptions. When you break these rules, when the city becomes either too congested or dangerous or the interactions are not worth it, this is actually Lagos. It's going to be the largest city in the world, so this is not fair to Lagos. Or they become too spread out and the city effectively becomes several regions of interaction. So this is kind of starts to be predictive of a lot of things, okay? And so now I'm going to throw data at you. We've done this for many, many, many countries, but you can see something like GDP if you're interested in in the economic size, the size of the economy of cities, what's magical is that this predicts essentially that larger cities should have larger economies per capita. According to that, with that number is predicted. There it is. There's Paris and London, almost the same size by this measure. Urbanized area, employment is more or less proportional, and so on. But what's magical about this is that this starts appearing everywhere. This is China. China's a little noisy, partly the data, but partly also, you see that these are the predicted exponents, these lines, and these are basically what you observe. We think that the data is bad here, but it's interesting to ask what was happening there. This is the US, which was the first place to which we did this. This is actually the surface of roads, which is more closely related to what the theory predicts. And this is, again, GDP. Okay, same number. So this is quite amazing. So we kind of have now a structural theory of how cities work. They're essentially social networks mediated through space. And this predicts structures that we see. I gave you 3 examples, but you see everywhere. Okay? Now, if you have a theory of something, you should take it for a spin. And so we did. I had a very good friend, Scott Ortman, who was an archaeologist. And so we started, for example, looking back in time. So we went back to look at many cities of the past. So we did cities of the Incas, cities of the Romans, some settlement systems in China. The data there is not very good. Many others. This is the Aztecs and the people of the basin of Mexico. But basically, the story, this is one example. But what we see is that cities of the past go back a long, long time until basically they break down eventually. I'll tell you how. But cities of the past worked in the same way. Now, they were less productive per capita. They were not so big. But they were put together essentially as spaces of interaction along the logic that I'm telling you about. So this is amazing, right? I mean, think about this. You can start predicting cities all the way back in the past. And this starts allowing you to say what kind of infrastructure they had, how many people somebody would see in a day. You know, potentially if you knew a little bit more, I mean, what did they do with their lives and so on. And this has to do also with how many professions exist and so on. Okay? And this is just one example of, so this starts becoming more productive of many, many ideas that you can start hypothesizing and testing. So this is a study we did with colleagues who are psychologists. And the idea was, it's well known in psychology that people that have more social interactions, larger social networks, tend to have less depression. So we said, well, you know, in cities, people are supposed to have more interaction. So what about that? So this is for US cities, and, you know, at this scale, it's quite predictive. But it also starts asking other questions, right? Within each city, you know, of course, that some people are lonely and isolated and segregated. So you can go there and see what happens. So we're doing that work now. But you see that the city is not just an abstraction of something that exists in the built environment that we design. The city is in you. It's the kind of social networks that you have, how you feel about it, how you're motivated to do the things, what you can and cannot do. So these things are related. And we now essentially have a somewhat predictive theory with all these components that allow you to do that. Okay? So we've done this for many places, many historical settlement systems. What I want, so you can see this in the book or in other places that we wrote, but I want to point down where this breaks down, because any theory should break down, right? Otherwise, you do not have a theory of everything. It breaks down before there's permanent settlement. We've done this also for ethnographic hunter-gatherers. You don't have scaling the same way. There's a transition from non-permanent settlement to permanent settlement that happens that's special. That requires both resources and institutions to happen. It doesn't happen in slums. So in places that are informal, you typically have more people and not enough infrastructure. You know that. But basically, this connection between the infrastructure connecting people is not there. And it also happens in reverse in shrinking cities, so ghost cities, cities that have too much infrastructure for the people that they have. These become very expensive and often start spiraling down because it's very hard to pay for that infrastructure. So you see this in Rust Belt cities like in the US. So this allows you to start seeing things that you may be interested in urban planning, in policy, in terms of what kind of human nature do we have, and so on. Okay? So I just want to orient you a little bit to where we are and point you, I got this question a lot, including in the last 2 days, what's the holy grail of urban science? What is it that we want to discover? So all of you young Turks want to go and find out. I'll tell you what I'm working on. So this is kind of, this also answers another question, which is we've been discussing a lot, and Mike likes to say, there are many sciences of cities and many different scales, perhaps, and for different things. And that's true. But there's also a unifying framework that I'm trying to tell you about. So for example, we have theories of systems of cities. This is really the origin of geography and planning, and Mike really is one of the world experts on this. They give you things that, if you're quantitative, you know about Zipf's law and gravity law. They were implicit in some of Mike's models. Then you have the scaling laws that I was telling you about. But these scales, where we start getting closer to people of neighborhoods and differences and inequality and cognition and how people plan their lives and what outcomes they have to do with what happens over time and finer structure of cities. These remain, we know a lot about these scales because data is getting much finer, but these scales have a lot more local stories. And so there's a lot here that we're still working on as things are becoming better observable. But essentially, the theory that we have is progressed in some sense this way. And what we'd like to do in the future is to start that way, have enough of a theory of people. You're never going to predict everything about a person. That's not the point. But you want to understand why people benefit from interactions, what they do with them, how they plan their lives, how that promotes opportunities in their lives, and come down and understand what kind of systems actually channel those objectives, right? We're very close to doing that. But in any case, that's the kind of thing that mirrors the development of many sciences. You understand first the larger things, and then you go to the finer things. But that still needs to be done. OK. I want to finish just with a couple ideas, the sort of more current work, that have to do with more fundamental things along the lines of what happens to people and why cities are really important. Okay, so this is a slide by UN Habitat, the part of the UN that deals with cities. It's about human development. So this is the gold standard for, if you will, good quality of life. This is cross-sectional around countries in blue and cities in orange. And so what you see here is in almost every country, these are the largest cities in every country, human development is higher in larger cities. Now, a lot of people, including in planning, may tell you, I don't think so. My city's full of problems. But unless you actually go and study what's happening, this is also an average result. Doesn't mean that everyone's doing well. There are large disparities in large cities. But it means that cities actually are doing a lot of the work of creating human development. And when you start looking at it this way, you keep finding that this is actually a general characteristic. There's a lot of inequality under the hood, and that's important, and gets to the finer question of who accesses these processes and not. Okay? So we've studied this in US in great detail, and so I was telling you about neighborhoods. This is kind of showing you the kind of inequalities that there are. This is my city of Chicago. You can go see the map there. But I live here, and now I live here, But there are places in the city that are actually very different. And this is well known for Chicago. Chicago is a very segregated city with very different quality of life and human development across it. But you start understanding the places that create human development. Actually, universities and campuses are good at that. And the places that destroy human development. In the US, jails are very good at that. No surprise there. This is a paper we just released, but it's extraordinary data. It has a similar picture of going down to the local scale, but it's for the whole of sub-Saharan Africa. And it has to do with access to infrastructure. I told you that slums violated this connectivity of the infrastructure to people. And we have a measure of this. You can read the paper if you're interested in the quantitative details. But we basically created a map of every block in sub-Saharan Africa. We have population estimates for it, and we have sort of some of the first sort of at least systematic estimates of informality and development and street access across the entire continent. That will be the future of urbanization in many ways. And what you see, again, is a similar story. So what I'm showing you here are 4 measures of development. So literacy in women, these are quite poor places. Water and sanitation and wealth. So what you're seeing here is that as this measure here is the measure of street access. So basically whether the infrastructure is there or not. So when you do have street access, which is on this end, you basically have that people have much more access to all these things, which are both physical and social and economic. So in some sense, this is what cities do. They're complex systems where all these things are really connected. If somebody doesn't have an address and lives in very poor housing, they're very likely not be able to have access to other things as well. But the moment they start to have access to that, or they can sort themselves to different situations, cities are very good at creating access to everything else. Okay? So that's more or less the end of my talk. I want to say just a couple of things. The other argument for science is an argument for Singapore actually being able to have a project on cities, plural, not just about Singapore itself, But if you want to say something from Singapore to the rest of the world, you need, as Lynn Ostrom says here, a common framework. Something that allows you to organize what you see in Singapore, what you see in Chicago, what you see in Lagos, and say something about another city. If you think that your city is so unique that that cannot happen, if you don't have a common framework, you cannot learn. So you can do very nice applied work, but you cannot transfer that knowledge to another place, and you cannot accumulate knowledge. So that's the other argument for science. And this is my final argument. I do science because I want to be optimistic. We live in a world full of problems. But when you actually look at these measures that I'm showing you a little bit in the last few slides of human development, how the world changed, how it is actually today a much better place than it used to be, this cannot happen without urbanization. At least we don't know how to do it. We've never done it before. But this is, of course, Shanghai. I could have a picture of Singapore like this, right? Shanghai was even faster. But what's interesting here is that it's not just a built environment. This process took about 500 million people out of poverty, right, in China. It's still ongoing. There's a lot more to do. This is not sustainable. But it's an amazing thing that this is happening. And without understanding this process in a way that generalizes and takes you to different places in Africa and India, to all the places that are frontier of this development, we will not have a chance to actually guide those processes towards a happier and more fulfilled and more sustainable life for all the people on the earth that actually have a right to get there. So with that, thank you very much. And that was my talk.
Thank you, Professor, for that amazing lecture. I would now like to invite on stage the moderator for the evening, Prof. Lai Choi Heng. Prof. Lai is the Emeritus Professor in the Department of Physics, NUS, and also the researcher with the Urban Science team of NUS Cities and the advisor to the President of the NUS Research Institute of China. He received his undergraduate and graduate degrees in physics from the University of Chicago and joined NUS after spending 2 years as a postdoc research fellow at the Niels Bohr Institute in Copenhagen. He was the vice provost for the academic personnel at NUS and the inaugural vice president for academic affairs of the Yale NUS College. Please join me in welcoming him on stage.
Mike, you're supposed to... Right?
Yep. I'm not going to talk last. So I think we have two exciting talks, and I think we appreciate both speakers are willing to stay behind for a little bit of time for questions and answers. We are not trying to engineer any kind of questions, so please be spontaneous and ask whatever that comes to mind. Anyone?
First question is always the hardest.
Yes, please.
I'm trying to reconcile Michael's and Louis. One is very digital twin, which is very technology, while Louis is more people-centric and so on and so forth. Right? So again, how can we put them together?
Well, we do have, I think we have different starting points for sure.
Yeah, completely. As you said, Louis, I talk much more about models, basically, and I suppose by implication simulation. But I think that some of the pictures I showed, if you unpack them, weren't a million miles away from one or two of your pictures. Right. A lot of movement, graphs, etc. Some of those examples, you could unpack them at that level. So at one level, we're both dealing with the same phenomenon, slightly different representation, maybe yours was a bit more abstract and so on. So there's an obvious connection there. The connection through how we use them, well, I suppose I implied a little bit, but not that much. And again, the same in that sense. So if you're looking for how you use this stuff, then probably these are not the two talks to kind of energize you in that sense. But I think they're much broader issues.
Yeah, I think the message is that, in part, we have a lot of data and we can model. But, and I think Mike's models had, you mentioned briefly, some of the same ingredients that I was talking about in them. But what I'm doing is interrogating those ingredients, asking to what extent can we measure them? Are they true? Are the assumptions right? And are the models predictive of things we observe? That's how you close the loop of science. I think to some extent they are. But, improvement in this kind of thing has to be subject to the usual test of being empirically validated or falsified. And I think in planning and this kind of large-scale modeling and so on, that, and there may be various questions that you want to ask of the models, you need to do that. And I think the kind of studies I was showing, this understanding of the social networks, how they're mediated through space, how changes in space may affect costs and so on, they allow you sort of a finer picture of how then the models may be put together. So that would be the way to connect them. I think we have somewhat different styles that just reflect where we come from.
I think there's one thing that does differentiate it a bit, and we've talked a little bit about this. To some extent, I'm not sure that anything I said implied there was some sort of deeper theory in some sense about how the world works. It's not that I said there wasn't, I just don't know. But in Lewis's context, I think, elements of that deeper theory were there, basically, in terms of how cities are structured across a whole hierarchy of scales and so on. I'm not sure that comes out particularly much in my own talk.
I'd like to think that it's possible to come up with such a theory. I gave you some ingredients of spaces of predictability that are more or less mesoscale. And I told you that there's a challenge still in going to smaller scales. But I do believe that it's possible. Now, many of you that are not trained sort of in these traditions may think, oh, how could you possibly think about modeling people, modeling cities? We're so unique and so on. We have medicine, we have other things that are very predictive, but they're not specifically predictive for everyone in every circumstance. There are also changes. So all these theories, in some sense, have a statistical component of a certain amount of averaging and a certain amount of contingency. And part of what's interesting is to explore that and to see how fine-grained can you go to acquire more predictability. I'm excited that we see in these theories of development as we go and ask that question that many things are interconnected, which is not the traditional approach because people often think of it as a purely economic process or purely public health process, but we see these things intermingled.
Yes, please.
Maybe to follow up from this. I'm a psychologist by training, so I'm intrigued by somebody who wants cognition in the room, right? So one thing that struck me with the two presentations is that you do modeling and theorizing for different purposes, and that seems to somehow reflect also your backgrounds, right? In which your work generates these amazing, highest quality papers and lots of foundational insights that were not there before about really mechanisms underlying it. But with Mike's examples, I feel there's a lot of what has the relation with design, and at some level planning has a design component. And I think what comes together in NUS cities and in other activities in the city space in Singapore is this matter of for what purpose do you predict? Do you predict to understand how the world is, or do you predict for what's basically counterfactual reasoning, figuring out of what could be? Because the designer always has to figure out the other options, right, and test those against one another, which also differentiates medicine and design to a large extent. And I was wondering, in the context also of something like NUS cities, how does one bring together this applied perspective that comes with design together with the science and engineering perspective? Mm-hmm. Governance that has to bind it together. What are the mechanisms that we need to have the models that the two of you built become fruitful for society?
I think it's an excellent question. I think they're not the same thing, as you say. I think it might help me to point out, for example, I don't know, that when you think of being an engineer of a certain kind, you need to learn physics, but it doesn't determine what you do. You need budgets, you need the materials you're working with, the context, and so on. Same thing would be true somewhat in medicine. As you apply things, you need to know biology and physiology, but and I think that we've not had sort of, I think we've had a lot of design, that was my implication, without having maybe a finer understanding of people and social life. And I think some of the work I talked about, I hope, allows us to have a better sense of that. I think a lot has been written about that. That's very insightful. But I think we have a lot of firmer evidence about that across contexts. So I think that this relationship with design is just being, will be amazing to think. I work also with beta designers, and a lot of designers are interested precisely in this, people-centered design, how you actually think of a city from the perspective of the person rather than from the perspective of the built environment and the bird's eye view, right? So I think in that sense, design is asking some of the questions that we're asking more in urban science, if I may use that term, but one is not the other, right? They need to talk to each other in terms of the solutions and designs they propose.
Yeah, I think in the context of the digital twin idea, there is something a lot deeper in this, and it relates to prediction. I think we need to re-look at prediction in general, I think, across all the sciences, all the social sciences too, in the sense that as we've learned more about how we can not predict, basically, or how bad our predictions are. I remember in the 1970s, I think, when I was a lecturer at Reading, our professor was Peter Hall in those days, and he would always pick up the latest stuff, and he came in one day and he had the Hunt report on trunk road assessment, right? Now, trunk road assessment is like A1, A2, all that sort of thing. And what this committee had done in the British government, it had looked at a whole series of transportation schemes since the 1940s, and it had a catalogue of how good the predictions had been. Yeah. And they were absolutely terrible. They were worse than terrible in that sense. And this whole notion of whether we can predict or not still drives us in some sense in terms of our models. Now, the digital twin thing, if you think there's more than, it's a bit like saying there's more than one way of prediction, basically. In some senses, that's quite useful. Now, I've not thought enough about how that kind of idea maps onto this bigger picture that Lewis is talking about. And it might make it quite useful, Lewis, for you to say what you believe in prediction. I'm fairly skeptical about it. I very much believe in the notion that many people have said it, although we can't predict tomorrow, but what we can do is invent it. We can invent tomorrow, but we can't predict it, and we can't predict what we're going to invent, basically. To some extent, it's a sort of that contained in those sort of cliche, that statement, is this whole notion about how we should use models to help us design a better future, really, in that sense. And I know that when people say, oh, these models, they're no good anyway, look at the Hunt reports, all this, they're no good. Why do we use them, basically? And then one falls back on this kind of hackneyed sort of phraseology. Well, we use them so that we can organize the debate about the future. It provides a framework to hang our ideas on. Now, I've said that for many years, basically, and it's wearing a bit thin to some extent. We need something a little bit more about the limits to prediction in our world, I think, in that sense. And that will help us actually how we can begin to use these. I mean, at one level, there's quite good reasons why, local planning authorities in Britain don't use this stuff. And that's part of it. I mean, generations of town planners in Britain have been trained on the fact that we can't predict, but that doesn't mean to say that we can't actually do something about the city, basically, in a sense. So to some extent, all of these ideas sort of point towards some of these issues that we've not really been discussing, but are certainly relevant to debate.
I have a go at that. I think Mike and I see it a little different on this point, but I think as we discuss, you'll see what we mean both. I do think that people are actually very predictable. But you have to ask the right questions, Insurance companies, insurance is a nice business, right? Why does it exist? Well, people are predictable. I can predict that you're going to have lunch tomorrow. You're going to have lunch. You're going to sleep somewhere. So the things are very constrained, right? This is the basis of prediction in any science, for physics, energy conservation, conservation of mass, and so on. For humans, is a basic physiology and things that we need to do. So what I was talking about in terms of what gives us predictability and the things that I was showing you, is that people live somewhere, they need to move around, they need to have interactions, they need a few things. They need, in a modern city, they need economic relations, their health is important. There's a bunch of things like this that are essential. They're always there. And, they're quite predictable. It doesn't mean they're absolutely predictable for each individual in a fine time, but certainly on the average, that must happen. I think there are things that are much harder to predict, questions of taste, questions of very individual, things are less constrained, and so on. And as I pointed out, in some sense, aggregate behavior is easier to predict. Predictability about development over long time horizons is harder. But I think that we're seeing there are actually a lot of patterns that when we bring large-scale economic trends or health trends to built environments, to interactions, that provides a lot of constraints that are necessary, that allows us to build back up to those. So that's more or less the exercise we're going through, is trying to bring that. And it's basically where urban science shines, because it allows you to materialize, to give substance and structure to a lot of processes in the social sciences that we've approached rather abstractly to date. So I'm optimistic in that sense. We have to ask the right questions.
Yes. You then, okay.
Okay, so as an urban planner, I think about UK or European cities or American cities and Asian cities. I think one thing in my perspective differ is like the scales, and especially the street blocks are smaller in Asian cities and maybe bigger in American cities and maybe European cities somewhere between. Correct me if I'm wrong. I think I'm bringing this up is I'm curious for both for both speakers when you are either thinking about modeling digital twins or you're thinking about like trying to finding the behavioral patterns. How do you think we should take the cultural background into considerations, or do you think we need to take that at all, or like universal modeling or theory should apply for every single culture?
Yeah, I mean, so we talked, both of us, a little bit about complex systems, but cities are complex systems in the sense that they're historical systems. They have a history. A city, Singapore today, is what is a changed version of what it was yesterday, and so on, right? So you cannot just pretend that doesn't exist. So when you have a certain structure, whether it's the size of blocks and so on, those can be transformed, but they exist within a tradition, and people are living in that structure. So they used to, and they know a certain structure, so you're not completely flipped at. So that's important, but at the same time, there are certain functional characteristics. I think in the US, I don't think it's quite true that the blocks are necessarily larger. I think cities that grew up, historically, it were created as people walked. They tend to have a finer grid and so on, right? And you find that within each city that often you have a walking part and then you have a suburban car-driven part. And indeed, you see that the transportation and movement determine a lot of those scales, at least if they were allowed to come together in terms of being harmonized. And that's more or less the argument I was giving you in general, but that then brings that argument to an historical place and a culture and allows you to start answering that question. There are other things that are important or not that have to do with what people are used to, what institutions they have, and so on. They get a little bit more complicated.
Yeah, I mean, I think that everything we do is culturally bound in some sense. I mean, Mike from NUS showed a picture yesterday in our talks about, he was talking about retailing in different town centres. Then when we went to look at some town centres, and the picture was of a British town centre. And perhaps I was the only person in the room who could say straight away, that's a British town centre. I didn't know where it was. I thought it was Cardiff, but I wasn't absolutely sure. But I could probably go to 50 or 100 places like that, and they'd look the same. And they're the same because of cultural laws. The way the chain shops purchase their sites and so on, the way the local authority does things or not do things and so on, are all culturally determined issues, which we tend not to question in some sense. So there's culture everywhere. Indeed, even me building a model compared to people in Singapore in the URA or in Create and so on, are building a model of transportation flow. Things would be different in a British context, and that's why I think that's the problem we have to deal with. The fact that our tools and techniques definitely need to be tuned in a particular context, and which seems to suggest that they are very specific and very idiosyncratic and very peculiar to the context and can't be generalized or translated. Now, I know Lewis has thought a lot about generalization of the sort of science that was talked about to other cities around the world, etc. But there are certain things that aren't generalizable. And how do we reconcile these idiosyncrasies with the generalization? Because to some extent, the idiosyncrasies, or the differences, I should say, are culturally bound in some sense.
Yeah, I mean, if you ask what language do people speak, what's their slang, what's their food, that varies a lot, right? If you ask the size of blocks, do they have streets, do they have houses and buildings, very conserved. So I think again, you have to ask what the question is, and so for some things that cultural history matters a lot. The other thing I would like to inject a lot of life into this question, is that actually large cities, very large cities in each nation, have their own culture, or at least they're quite alien to their nation. New York, most Americans kind of gasp. Tokyo, most Japanese kind of don't recognize as Japanese. So a lot, there are cultures that are created also locally as cities change and so on. So there are levels of this, right? And there are many subcultures in each city and so on. So it's a very dynamical process, and this has been also in sociology mostly and anthropology been discussed. To what extent, how diverse is a city, and why is it that large cities support such large diversity? And some of that has to do with the nature of these social networks that actually allow those processes to exist in terms of specializations and interconnections, but some of it is also that there's space for that to persist. But, there are a lot of questions that are very contingent, but there are also, what I want to emphasize, there are a lot of questions that are very conserved.
All right. Sorry. First of all, thanks for the fantastic presentation. And when you talk about urban science and the digital twins, you talk about the modeling. But for the modeling, the first thing you need to do is to prepare the data. But the the hardest things for the, especially for the small research group, is to get access to the data, especially the high resolution data. So I have the questions about how you do. It's possible to address the data challenge, because I know the high resolution data, the research group need to pay a lot for it, and it is not compulsory to open access. So it is possible to get addressed the first setback. And also I know we have the volunteered geographic information that individual person to upload it by themselves, but that data have a lot of spatial bias and still hard to mitigate. So my question is how you get us to get through the data challenges for the urban science or the digital twins.
I think this is a rather technical question, availability of data. Maybe we go over that quickly.
Do you want to go first?
Sure. In some senses, Louis showed a picture, Le Corbusier's New Radieurs, basically, where I don't know what data Le Corbusier had to actually produce that plan, but 100 years ago, urban planning was full of visionary statements like this. Without much data, I may be doing them a disservice at one level, because that doesn't mean to say they weren't thinking about the world in any sense, but the data wasn't readily available. And I think in my lifetime, the data has got better. I mean, a lot of the data we use is from the Office of National Statistics, who've successively, every year, produced much better data by looking at, and this is by and large, they collect data on 100% sample, basically. The national census, like probably here, is where you have to fill it in. It's mandatory to fill it in. And so that kind of data is what we consider to be gold standard. The basic problem is it's expensive to collect, and it's only done once every 10 years. But actually, that's not quite right, because there are updates and samples and so on all the time that the ONS are doing, basically. So that's good data. But there's a lot of missing stuff. In Britain, we can't ask the census, we can't ask the income question, basically, by law. Parliament won't let us ask the income question, but therefore the Office of National Statistics reverse it all from tax records and things like that, and get some quite good data. But nevertheless, I think you're referring to a lot of new data which has come on stream, which is enormous, real-time stream data, basically. And that is very problematic. I think we're only just beginning to get used to what that data is. That if you go to a conference on mobility, for example, you know, 90% of the papers will be on analyzing sort of, you know, traffic from mobile phone data and apps data and things of that sort. I think we have to be very careful about this, but we are just learning about those data sources and how easy it is to unlock them and how easy it is to extract what we can't get in another way by direct observation or other kinds of sensing from that thing. So there's a new world, I think, and this is very much to do with the smart city, you know, the 24-hour city, all this sort of business in that context.
Yeah, I'll just say two things quickly. The first one is that in terms of data is never perfect or complete. You have to know its limitations, but it's getting better all the time. And certainly for us who've been in the game for a while, data is just amazing compared to what we started with. But the second thing I want to say, which is more important, is data should not be the driver. You know, if you're doing anything in science or that's predictive, you have to have an idea. What's your idea? What's your question? That's the most important thing. Because there may be data that speaks to that question or not, or maybe it's a bad question, or it's a question that cannot be decided now because the data somehow is not there. So I think that asking the question, it goes a little bit to these questions of what's more contingent and what's more predictable, is the most important thing. And then you can chase the data, know when the data is coming and so on, and know what you have to do to the data and how good it needs to be in order to be able to have an answer. So the data is never perfect, but if you have good questions, then you can start answering them as you go, or good models that you do. So I always say that data should always be future-oriented. When it's created, it should be about what we can predict into the future. Because without that, you're just being a data jockey. You're just describing data. A lot of people, you know, data is big, you can do that. But to me, it's a little less interesting. I'd like to be able to learn something from the data that's not in the data.
Okay.
Can we take a question from Zoom?
Can we take a question on Zoom afterwards?
So this is a question from Joshua Vargas from FCL. He's very curious about Prof. Batty's and Prof. Bettencourt's views on how these emerging ways of studying cities would interact with urbanists in the social sciences who have their own approaches and disagreements on how to understand processes like urbanization, and whether general theories are even possible in the first place. Are they complementary? Can they work together, or do they answer entirely different kinds of questions altogether?
Big question. I mean, there are many people thinking about cities and studying cities, so you have to respect the plenitude of that. And I think that we all have to learn from each other. I think to the extent that then our objectives may be different, right? So if we want to, we're interested in different phenomena, we may be interested in predicting or knowing about different things. I'm interested, as I declared from the beginning, in having, when we talk about general theory, it's a general theory of cities, but it's kind of a theory that needs to be filled in, you know, gradually. A lot of social scientists, forgive me the generalization, but they often work with local theories at the level of neighborhoods or individuals or cultures and so on. There's sort of more local places where there's more contingency and so on, and therefore we need different methods. But at the same time, as I hope we can see, there's certain generality to human behavior and to the structure of cities and so on that should inform more contextually in local studies. So I'm hopeful that we can all, you know, live together and share ideas, but sometimes work at different scales informing each other. We use a fair amount of ethnography and people who do social work and community organization and so on as we go to the neighborhood scale, and also then psychology and observation of behavior when we go to individual scales. There's a lot of work that we're doing now in collaboration with people working at that scale.
Yeah, I think I think this is part of this general question of how, you know, science of cities or urban science maps on to other disciplines, other approaches, other perspectives. And clearly and we talked about this in our discussions with NUS yesterday, there may be many sciences of the city in that sense. But more importantly, science of cities or urban science is not something that is isolated in any sense from, you know, everything else that's going on. And as Lewis said, there there are many different perspectives on cities, almost as many perspectives as there are people thinking about cities, basically, in that sense, or maybe living in cities, and that means everybody. So in some senses, our kind of view has to be related to that. But I think there are some very strong anchors that can relate what we've been talking about this afternoon to other social sciences in this particular context, which do have general theories pertaining to them in some sense, perhaps qualitative compared to quantitative in the sense that you can't necessarily write down algebraic relationships and so on in this particular context. So I think there is a big job to be done. And, you know, I'm old enough to know that I remember when in the 1960s that all of this quantitative geography came onto the scene, you know, Peter Haggart and so on. Of course, David Harvey basically was a quantitative geographer, and he was part of that group from Cambridge. And I remember him coming to see us in Reading to give a talk, and he just published his book, Social Justice and the City, which basically threw everything up in the air, basically, in terms of the quantitative revolution in that sense. So, but Harvey didn't necessarily think that all of that stuff was no good. He basically said there are different ways of looking at the world, in a sense. And I think that's what we've got at the moment. I know in my own institution, you know, the Bartlett School of Planning is much, much bigger than our unit in CASA, for example. We've got, out of 20 staff or something in CASA, you know, 2 or 3 of them are town planners, basically, by background. But if you look at Bartlett Planning, the vast majority of them are social scientists. They're not planners per se in that sense. But that's part of the scope of all of this knowledge that has expanded over the years. So how to put it together in one thing is almost impossible. That's why I'm more skeptical about there being, you know, a grand theory out there to being discovered. I'd love to think there was one, but I'm not sure, basically. I just don't know.
Well, it's a matter of, you know, scale and detail and contingencies and questions. All those things vary. What I think I would like to flag as sort of a stronger position, besides being very open to all perspectives that I want to share with Mike, as he said, is that when somebody says, "Oh, this cannot be done," we'll never know how to predict people's behavior or understand. I mean, why not? People say that of every science, right? Of physics, of biology, of medicine, you know. So, you know, the point of science, the point that I was making is that it has to be respectful of knowledge and the phenomenon, and it has to proceed step by step, asking questions, seeing how much it can understand or not understand. And so in that process, we will find out some things that are very hard to predict, and maybe they're completely contingent, and other things that actually are quite predictable. And that's the way to find out. But if you stop yourself from embarking in that journey, then we sacrifice knowing a lot of things that are important for us to know, even essential to human nature, but also to the future of our societies in the next few decades that are so critical.
Okay, I think we have already overshot our time by 10 minutes. Maybe one last question?
Right. I'm an engineer, so I already talked about digital twin on the technology side of it. But this duality, so my question here is, yes, people need to get connected and all these things. So you need technology, you need energy, all these things. Now my question to you is, at the end of the day, we look at people are happy or not. So the question is, if we get more and more technology, more energy, are we becoming more happy? Yes, to a certain extent. Now, will there be a most efficient point beyond which you increase the technology, then people will be really bad and then they will start becoming unhappy? So has there been any study done on that optimum point where we should not cross the
optimal point of happiness? I don't know that we know what that is. You know, I don't think Corbu asked whether people are happy. And I think we have neither, Michael. I don't know. Happiness is very hard, actually. Depends on the question when you ask people. I mean, you know, cities are open systems. People come and go all the time. And so the people that are there, by and large, I mean, here your nation is a little different. But in most cases, people that are in these environments, either a larger city or a smaller city, they do this all the time. They change their environments through the life course, very typical. Young people like bigger cities, if they're more educated in particular, then they move out. So these environments perform very different functions in people's lives, and there's sort of usually a dynamics to what serves people better or worse. There are people with fewer choices, we should acknowledge that, and that's part of the problem of planning. But I don't know that there's an answer to the question you're posing. I think that cities perform a lot of important functions in human societies and in human lives as channels of opportunity, even though they always come with a struggle. And I'm not sure if people are more or less happy, but they usually choose to be in these environments or not be in these environments. But as you know, worldwide, more people are living in urban environments. So presumably, I choose to believe, maybe unlike some other statements that people sometimes make, that they do that with a choice and with knowledge, at least with hope for the opportunities that are opening up. I think that's a part of happiness.
Well, I don't know. I mean, I think I read on the BBC website in the last few days that the Swedes are the most unhappy people in the world at the moment. But on the other hand, even less recently, but within the last 6 months, I've read sort of the Finns, basically, in Helsinki are the happiest. It's a tricky one, but I think one of the things we haven't really discussed, I suppose, that's implicit in a lot of this is and it's implicit to some extent in my talk, the whole nature of how society is changing in terms of technology is really quite profound, really, in some senses. That, we now look at the last 250 years, it looks like a continuing technological revolution. It's increasingly difficult to separate the bits out. You know, there's certain dominant themes and so on at certain times. And to some extent, that's due very much to computation, the fact that so much is being computed in this particular context. I suppose at one point in the talk, I said, you know, back in the early 1950s and so on, people were talking about living inside computers, basically, in that sense. So I think that's a very important issue. And the speed of change is so great that it could make people very unhappy. I'd be interested to know whether any surveys have been done of technological revolution 50 years ago and now, whether there had been a change in some sense in our ability to actually interact and to absorb these new technologies in that context. I think that's quite important. It's certainly important to the way we work. And, you know, without computers, you know, we wouldn't be here today just talking about this sort of stuff, basically, in that sense. So I think happiness is related to these broader currents in society, too.
All right, I think we have really come to the end of the session. Let's thank both the speakers.
Thank you, everyone, for attending this event and actively participating with your questions. Please watch out for our social media channels, where we'll be informing you about any other further events. Thank you, and have a nice night.